Just a minute. So we'll start spherical mirrors today. Why they are called spherical mirrors? Because these mirrors are not plane mirrors. What we are going to do today, just I tell you, we'll be doing this part, reflection of light on plane surface we did. Today, reflection on spherical mirror. We'll learn sign convention, we'll define focus, optical center, we'll do linear magnification, magnification of area. Mirror equation to be established to solve practical problems. We'll define magnification also. Magnification produced by a spherical mirror. So what is a spherical mirror? You consider there is a glass sphere. If a part of it is taken and then either inner side or outer side is polished with silver, then a spherical mirror will be formed. So this is imagine this one is a sphere, this is a part of it, sphere. Don't think that this is the line segment. Then this portion will behave like a mirror, and that mirror can be convex or concave. As this sphere has a center of curvature, center of the sphere is there, that center will be considered as the center of curvature of this mirror. So how to make a convex mirror? For a convex mirror, this part, inner part, is silvered. It is convex towards the rarer medium, and when it is convex towards the rarer medium, then just we are taking the part here outside this sphere. This one is a convex mirror if this portion, I have taken a bigger version of it, same thing. This is called aperture or diameter of the mirror. This is a convex mirror. Okay, this one is a convex mirror. This center of curvature will be taking here. Actually, it is center of sphere, center of curvature for the spherical mirror. And if you consider a line segment joining A and B, that will be considered aperture. Aperture or diameter of the mirror, of the convex mirror. How to get a concave mirror from there? Imagine we have taken that part from here. can take from here also, but this time we are taking the part and silvering this portion. Then you detach it from the remaining part of the sphere and we'll be getting a concave mirror like this. This portion is silvered, center of curvature lies here. This is center of curvature for the mirror. It is just centered for the sphere, and C stands for center of curvature of the mirror. This is for the sphere, glass sphere. For this glass sphere, this is center, and for the mirror it is center of curvature. Clear? So this one is a concave mirror. Clear? So for this concave mirror also we can define the diameter or aperture of the mirror as this one. This is diameter or aperture. Okay? So aperture is the line segment joining two extreme portion. Midway between these 2 points on the curved part, that is called pole. This part is pole. Pole will divide the upper half from the lower half. Imagine, and if we join a line segment through C and P, that line segment will be referred as the principal axis. If a line segment is joining C and P, this will be referred as principal axis. So PC is said to be the principal axis. Clear? Understand? So there is no confusion in diameter, aperture, center of curvature, pole and the principal axis. Principal axis is the line segment joining center of curvature and pole. I will be discussing the sign convention for a spherical mirror, because when you are going to define, just take one example how image is formed. Let me explain. We have taken this convex spherical mirror. How the image will be formed? Let us do one experiment. How can you form the image? Center of curvature lies this side. For it, center of curvature always positive. I'll tell you why. Now this is the pole, this is center of curvature. You have joined these two by a line segment. This is the line segment. Okay? Joining center of curvature and pole. How the image will be formed? This is very important. Tracing of image formed by a mirror. Clear concept should be there. This will obey the law of reflection. This we should keep in our mind, because we are considering reflection on spherical mirror. A question automatically arises when you are defining the angle of incidence, normal drawn at point of incidence, the incident ray, the reflected ray. This is incident ray, this is the reflected ray, and this one is the normal. Question arises here, if this is our incident ray here, this is reflected ray, and this is normal, how can I draw normal for spherical mirror? My answer is this. Suppose you are taking a ray coming from some distance, say it is coming from some distance away from it like this. Just let me take this one as, yeah, ray of light coming this way, incident here. Okay. Now in what direction this ray of light will go? If A is the point of incidence, and if you join these 2 points, imagine C to A and direction of light matching. I mean same thing, it is going this way, then it will be reflected back in the same direction. Got the point? C to A, this is the normal. A light ray is directed towards the center. Towards the center. What will you observe? It will retrace its path back. It will go back in the same direction. Light ray you are allowing to fall this manner, a ray of light, and then a ray of light, this is incident ray, a reflected ray will go this way. Why? No bending will be there because it is directed along normal. In case of plane surface, if you send a ray this manner, then as I told you, this will follow the same path in backward direction. This is a plane mirror. Law of reflection obeyed. Regular reflection we are taking. This is I, this is R. In case of spherical mirror, ray sent towards the normal, it will retrace the path backward. Clear? This concept you should keep in your mind. But if the ray is not going towards the normal, then what will happen? That case is very interesting. Imagine we are sending 2 rays this manner. One ray directed this way, another ray directed this way. Okay, these 2 rays are going this manner, and this is a convex mirror only. Then these 2 rays supposed to meet at a point. You should agree with me. These 2 rays supposed to meet at a point where? On the principal axis. But due to this mirror, it is not possible. They are supposed to meet at a point. So this point going to be what? This point going to be the position of virtual object. This I showed you last class also. On a plane mirror, rays are being incident this manner. Just take one example here which I showed you. One ray going this way. Past session you must have seen, I have explained the object is virtual but the image is real. I just remind you again. They are supposed to meet at this point. Here, this is virtual object. But after reflection, going this way, it is going this way, they will meet at a point on the, just take it a straight line, they will meet at a point here, that will be the position of the image, isn't it? So image is there. If object is there, this is virtual object and this is real image. Same thing will happen there also. But how the image is going to be formed, that we need to discuss. It will obey the law of reflection, you know. So let us draw the normal first. This is the center of curvature. C is taken here. Draw the normal here. Be careful. Just a minute. It's like this, like this. This is normal. Center you take bit away. Let me explain. This is center, and here also normal you have to draw at this point also. This point is say A, this one B. Normal you have to draw here also. This is normal here. C to A and C to B. It will suffer reflection over there. After reflection, it will obey the law of reflection only. Light will go this manner here. Light will go this manner there. Okay. So at this point you will get the image. This object is real and this object is virtual. This is virtual and this one real. Okay, keep this one in your mind. So real, virtual object, and we get real image over there. Sign convention going to play a vital role over there to establish the relation between this object distance, image distance, all these things. But before we do that, let us make few more observations. I hope you all are ready with the pen and pencil and doing it with me. Take some time, get ready with your pen and pencil. Now an object lying on the principal, this is for convex mirror. Okay, for convex mirror we have done this. Let us take the object on the principal axis, then see how image will be formed for convex mirror. For a convex mirror, taking a bigger one, but never take very big diagram here. I'm just taking it for explanation purpose. Object is here. Okay, how the image going to be formed here? You take a light ray, it is incident here. Last class I told you the object to be real if at least two rays are coming out, isn't it? Or it is virtual object if at least two rays supposed to meet over there, isn't it? So I mean appear to come from there. So here if a light ray going this way, to get the incident ray we have to draw the normal. Normal drawing is very important. You take center of curvature there and draw the normal. Center of curvature for convex, it will lie this side. This is the center of curvature. Draw the normal here. Okay, you take bit more away because I have taken bigger shape. Take bit more away. This is the normal I am drawing here. Yeah, this is the normal. Here also, this is the normal. Center, normal at this point, normal at this point. I have taken say this point, arbitrary point L, this one M. So light ray this time, it will obey the law of reflection. It will go this way, and here also it will go this manner, isn't it? Now if we produce this thing back, which one? If you produce this ray, this reflected ray, they are not meeting, no? So obviously virtual image going to be formed. How you can form it? You just produce it in backward direction. Produce this one also in backward direction. Yeah. This is going to be the position of image. Clear? So you need to send two rays from the object. So this time there is a real object, and you do it with me. I am doing extremely slow rate so that you can practice with me. This is real object and this one is virtual image. Alright, there is a real object, virtual image. because those reflected rays supposed to meet at the point I, we get the position of image on the principal axis. Clear? So all these we have done for convex mirror. Let us do it for concave mirror. So see how image and object formed. We are very much interested to relate this object distance, which will take as u, this image distance, which will be taken as v. So what is u here? This portion is u and this portion going to be v. Means I am telling you one convention right now, then we list all these sign conventions one by one. That is, distances are measured from the pole along principal axis. Okay? Either towards right or towards left, and apart from this we follow Cartesian sign convention. Cartesian coordinate system you will keep in your mind, then everything is done. Clear? So the real object, virtual image, real image, virtual object done in case of convex mirror. Let us go for concave mirror. For a concave mirror, what happens for a concave mirror? For a concave mirror, you just take the mirror this manner. This one is a concave mirror. This portion is silvered, that's why it is concave. And imagine there is pole, there is center of curvature, join them by line. This is pole, this is aperture, and you take an object on the principal axis. This is the position of object. Object is being taken there, here. This is the position of object. This is the center of curvature. Clear? Now, if we send a ray any direction, suppose I am sending this manner. Ray I am sending this way. It will obey the law of reflection. So, what you have to do? You have to draw the normal. This is the normal drawn at point of incidence. Cn1 is the normal, and ray will go this manner. You will see that if I send a ray this manner, it is coming this way. If I send a ray towards the pole, then it will retrace its path. Don't you agree? Yes, I agree. So this is going to be where these two rays intersect, that is going to be the position of image. Where incident ray and reflected ray meet, that is going to be the position of image. Keep this thing in your mind. So this is image. But some people will say that you only said 2 rays should be taken. If you take 2 rays, it looks fine. Then you have confirmed that it is going to be formed over. I mean, diagram will be more prominent like previous one. So what to do for it? Send a ray like this, the way you sent there, and on the normal, same manner. A ray will go this way, direction of incident ray. Normal you draw here. You do it slowly with me. You will understand everything when you do it on your own. Okay. Yeah, this is the normal here, CN2. Now the reflected ray will go this manner. Clear? They meet at this point. See? So you do two things. If you say that no, I will not take so complicated thing, I will send one ray towards principal axis, one ray arbitrary direction where they meet, that is image. I don't have any problem. Do it. Otherwise, take two rays this manner. And very interestingly to note that the image is formed on the same side of the object. In case of concave mirror, if this is U, then this part is going to be V, this one V. The image and object formed, image and object are formed on the same side of the mirror. It is formed this time. It may not form always, but here it is okay. Now problem will be there when we want to relate U and V in the previous case or in this case, because with respect to pole as origin, the position of image and object going to be changed. We have to formulate a fixed sign convention to relate all those things. Before that, let us do. So how do you name this? This is real object, and this one is virtual image. Sorry, real image. Why real image? Because the reflected rays, these are reflected, you know, this ray going this way, reflected the back this manner, going this way, reflected back this manner, they are meeting at the point I. So image should be a real. Is there any possibility to get a virtual image over there? Of course it is possible. But to get a virtual image, we have to change the position of the object. You see, object we have taken far away. That's why rays are coming this manner. But if I change a bit, then the image formed may not be real, it may be virtual. So this is the case of real image. Let us take another situation here. It is going to be spherical mirror this way, the concave mirror only. This is your principal axis. Okay. Take an object here at this point. Object is taken here. It is very close to the pole. Object is here. Then what will happen? Center of curvature lies somewhere like this. So suppose I am taking point of incidence, one point of incidence here, the other one symmetry here. So you draw the normals. This is one normal, this is center of curvature. And this is the other normal, CN1, CN2. Clear? Now from this object, if we send a ray, what will happen to the ray? Let us take a ray this manner. It will be reflected this manner, you should agree. Here also, if you send a ray this manner, it will be reflected like this, isn't it? Now you produce these two rays backward. this point going to be the position of the image. Clear? From object is going this way, at A reflected, at B reflected. They are meeting at the point I. So here object is O, object real. Real object, then virtual image. Here also U is the object distance and V is the image distance. This is U. And this portion going to be V. Alright? V is the position of the image. Now, we are going to relate all these U and V. So, image formation idea is clear now, isn't it? Now, for this point object, if you derive something, that will be true for extended object. Let me deduce the relation between U, V and R. Then I will show you image formation for extended object. Okay? So we are going to relate to find the relation between U, V and R. What R stands for? R stands for the radius of curvature. The relation, if we want to derive, it will be like this. Concave mirror and the principal axis. Okay, we are taking the object here, object at this point. We have to form the image. Center of curvature lies somewhere like this. Light is incident here. You must draw normal there. This is center of curvature. Sorry, just a minute. This is your normal. Center to that point you always have to do. Clear? L is the point of incidence. So now reflected ray will go by obeying the law of reflection. Clear? So it is going this way. I told you there are two ways. If you don't like to involve two rays over there, no issue. You send just one ray along the principal axis. We are discussing reflection of light. Light can't penetrate, so it will go back this manner. Isn't it? You send this way towards pole, but it will retrace its path. These two meet here at the point O. Sorry, I. This is the image. Got it? You understand the position of center of curvature? I'll give you the easiest proof. Okay? Only thing, one thing you have to keep in your mind, that these rays are paraxial. What is paraxial? Paraxial means very close to the principal axis. Aperture should be very small. Before you deduce anything, no. You should remember a spherical mirror has small aperture only. Clear? Spherical mirror has small aperture only. So this spherical mirror also has small aperture. These rays are paraxial because of this paraxial rays. Paraxial rays. Paraxial means they are close to, rays are very close rays are very close to principal axis, or rays make small angles. Rays make small angles with the principal axis. Okay? See how nicely we can make the derivation here. What we are going to derive? We are going to find out the relation between the object distance. This is object distance that I told. This we are taking as u. Aperture small. So this part is u. This part u. This part is going to be v. This part going to be v. Center to pole, that distance, this is radius of curvature. Quite obvious. You understand? U, V and R. Now, to find out the relation between these three quantities, my assumption was rays are paraxial. Means the incident and the reflected ray, they make small angles. This incident ray, suppose it makes an angle alpha. This reflected ray, suppose it makes an angle beta. And this one gamma. Alright? This one gamma. This is alpha, this part is beta, and this part is gamma. Clear? The angle of incidence be I here. Then this is also I. You must agree. Angle of incidence must be called the angle of reflection. Now, you have to do one thing additional, that is, you will be drawing a perpendicular here from L to the principal axis. LM is the perpendicular. P is the pole. Now tell me one thing. If the aperture is very small, is there any difference between M and P practically? No. So for a small aperture, MP tending to 0. For a small aperture of the mirror, MP is negligibly small. Clear? MP is negligibly small. Hope all of you can see the diagram properly. In diagram, what do you observe? This triangle, I am writing here, in triangle ILC. This beta is the exterior angle, you can see that. This is the sum of two interior opposite angle. Number one, this is not nu, my gamma and nu, be careful. Okay, this is gamma, we have taken gamma. So beta exterior angle equal to gamma plus I. At the same time, in triangle, this is ILC. Now I am going to consider ILO. In this triangle, what do you observe? Beta equal to beta, this thing. What do you write? You just change, you take CLO in this triangle. CLO, what do you observe? That gamma equal to alpha plus I. Isn't it? This is gamma, this part, gamma equal to this I plus alpha. Okay? Now, you subtract beta minus gamma equal to gamma minus alpha. So, alpha plus beta is 2 gamma, isn't it? We got alpha plus beta equal to 2 gamma. Now what to do? Now see, these angles are small. Now alpha for small angles. For small angles, alpha equal to tan alpha. Tan alpha is what in the diagram? I should not write with the red pen because red pen is not. Can you see the red one? No. So just let me change it. This one we have taken gamma. Why it is obvious? This is beta and this is alpha. This is I, this is I. Extremely sorry for that. Now for small angle, alpha is tan alpha. Beta is tan beta. That gamma also tan gamma. You just put the values. Tan alpha, tan beta and tan gamma. What will happen if you put you are putting in number 3. So from 3, if we put then tan alpha plus tan beta twice tan gamma. Substitute the value of tan alpha. You can see in the diagram it is Lm by Om. Tan beta it is Lm by Im. And tan gamma that is Lm by Mc. Now this Lm factor is common, you cancel. Okay? 1 by O to M, the distance is M and P are very close, I told you. So OM is approximately OP. IM is approximately equal to IP. You substitute the values. 1 by, now the problem arises. Just I tell you a practical example problem here. The object lying on left side, image lying on right side, or object on the same side. Will you take the same sign convention over there? No. My suggestion, you just remember Cartesian sign convention. P as the origin, towards right anything positive, towards left anything negative. Clear? Towards right anything positive. It's, you just imagine as if there is x and y axis. X axis directed this way, y axis directed this way. Then you decide the sign. If anything lying on negative x axis, it will be negative. Anything above y axis, it is positive. Anything below y axis, it is negative. Light you always send from left side. Along the direction of light from the pole, everything positive. opposite to direction of light, everything is negative. Clear? By Cartesian sign convention. So what should I put for OM? OM you can see in the diagram. O2M is what? O2M is U. But I won't take U, it will be minus U. Because light going from left to right, you are measuring from pole towards left. Towards left, anything measured, that will be negative. OP negative. OM and OP same thing. As OM is equal to OP, that's why IM equal to what? IM or PM? No. IM is different, sorry. IM or IP. IM is approximately equal to IP, that is V, but it is also opposite to direction of light, minus V. And MC. MC is diameter, no, radius, so it is minus R. See, just put it here, 1 by two by minus R. So 1 by U plus 1 by V equal to 1 by 2 by R. This is the relation between object distance, image distance and radius of curvature. Clear? So equation is established. I think I have not given you any trouble by simple consideration that alpha is tan alpha when alpha is very small. For beta, for gamma, tan of anything it is true, we have established. It's the simplest way of derivation. Class 8 geometry and then sign convention. Okay? So what is sign convention? It is Cartesian sign convention. Our origin is there. Anything towards right positive, anything towards left is negative. Image distance, object distance, anything towards left is negative. Clear? This relation you can establish for convex mirror also, but that will be your homework. Prove same thing, 1 by V, 1 by F, sorry, not F, 2 by R, 1 by V plus 1 by U equal to 2 by R. This is in which case? This is for convex, you will prove. For a convex mirror. Prove for a convex mirror. Clear? This will try, definitely will try. Same manner, same kind of ray diagram. Now automatically, in case of mirror equation, another term which is known as focus, focal length must be inserted. How to do? Now we are going to define focus for a spherical mirror. Focus. What is that? Focus of a spherical mirror is the point where it is parallel to principal axis, supposed to meet on the principal axis. I am drawing the thing. What is focus then? If you send a ray, parallel to the principal axis, ray or beam of light, then after reflection they will pass through what? Through the focus. Clear? If you send a ray parallel to principal axis, it will meet at the focus. Very interesting to relate this concept here, and this focal length where they meet, that distance we always take small f. So obviously it is going to be small f here. Now how can I relate R and F relation between R and F. How can we relate these two, R and F? See, very interesting. So, rays coming parallel, it means they are coming from infinity. So, for parallel rays of light, they pass through, they will pass through the focus after reflection. Okay, they has to pass through the focus after reflection. So focus is the point where if object is at infinity should meet. So focus going to be actually equal to what? Focus going to be actually the image distance. Under what condition? When rays are coming from infinity. So we can write your conclusion here. Therefore, focus is the position of image for a parallel beam of light. Clear? Focus is the position of image formed by parallel beam of light. So therefore, this is V. Therefore, so when V equal to minus F, where does U go? U is minus infinity. Agree or not? Object is at infinity. So V is at minus F, for which U was at minus infinity. So if this is our equation 1, then you put it there. See what you are getting, very interesting. F and R will be related. So 1 by minus infinity using this only, plus 1 by minus F is 2 by R. R is also negative. This implies F equal to R by 2. So in place of R by 2, we can replace F. So what happened to this equation then? This equation changed to 1 by U plus 1 by F equal to what? Just put it there. R equal to F by 2. No, R equal to 2F. You put there. It will be plus. So we are getting 1 by V plus 1 by U equal to 1 by F. This is known as Lenz's formula. So what is that? Lenz's formula is the relation between object distance, image distance and the focal length. Isn't it? So relation is done. Relation between U, V and F. Earlier we did relation between U, V and R. Here it is between U, V and F. This will help you to solve a problem. And remember, as you got this by sign convention, when you solve problem, we'll use sign convention once more to get everything back. Am I clear? On it, if we are going to solve any problem, we should keep this thing in our mind. Done? So your homework again ready? You do and send homework. Do it for a convex mirror. Now you have seen that in spherical mirrors, sometimes image becomes small, sometimes, oh, you haven't seen that, wait a minute, just do it one thing, image of an extended object, then we'll go to the next topic. Image of an extended object. So how image will be formed for extended object? You have to note it down. Okay? What is the sign convention for it? For it, the sign convention will be rays are allowed to fall from left side only. Distance is measured from the pole along principal axis. Distance is measured along the direction of light positive. Distance is measured opposite to the direction of light negative. Okay, let us do it. Image of an extended object we are going to do. Just do this one. For an extended object, object is here. This is the object. Its image we have to form. AB is the object. Take AB as the object. This is not also not coming very good form. So better you take this ink. AB is the object. Okay. How its image will be formed, this we are going to discuss. What concept you have to remember? Send ray parallel to principal axis. Then what will happen? It will pass through the focus. Alright? What we have listed before, what we have seen before, that we are listing here. Send ray, this is extended object. Its image we are going to form. Send ray parallel to principal axis. You better write the steps. Write the steps. Step number 1. To form the image of an extended object, we remember this convention. If a ray sent parallel to principal axis, it will meet at the focus after reflection. And another very interesting thing we have noticed, if we send a ray towards center of curvature, then it will retrace its path, isn't it? If we send a ray through center of curvature, sending a ray through center of curvature, sending a through center of curvature means along the direction of normal. This I told. Its path will be unlimited. It will go this way and it will come back the same manner. So this is the position of image. E dashed B dashed is the image. We have got a real object and real image, but real image has become inverted. Clear? The real image has become inverted. You understand the diagram? Diagram is clear? So what I did there, a ray sent parallel to principal axis, it will pass through focus. Send a ray through center of curvature. it will retrace its path. Where they intersect, from there I have drawn a perpendicular. This is image now. What will be the nature of the image? Nature of the image will be, it is real. This is real. Image real. Inverted and diminished. Clear? So, where have I kept the object? Object I have kept away from center of curvature. That's why image is from this manner. A dash B dash is the image and it is smaller in size. And in this case also, whatever relation you got for point object, it will be valid there also. 1 by V plus 1 by U equal to 2 by R, and R is 2F, so 1 by V plus 1 by U equal to 1 by F. Okay? So this relation is valid in case of mirror. AB is the object, A dash B dash is the image. Relation between U, V and F will remain the same. But one thing we have to take care. Okay, let me draw another diagram here where object, this time you will write object is beyond C. The image is formed where? Image is closer to the pole. If you draw actual ray diagram, if you keep it beyond C, it will be formed between C and F. Okay? Now we are going to do opposite thing. So this time psi of image is less than psi of object. Situation may arise this manner. I am just showing you clear diagram. You all must do it with me. Object is extended and we are keeping it, say this is focus, this is center of curvature, we are keeping it here. Understand what I said? This is the object AB. How the image is going to be formed for this object? What is the principle? Here we will send a ray. No, it was beyond C. Image is formed here. We are keeping the object now between C and F. Image will be formed beyond C. How? How it is formed beyond C? What you have to do there? This is B. AB is the object. What to do? The first step, send ray parallel to principal axis. Oh my god, I have written F twice. This is C. So this will pass through focus, isn't it? Send a ray through the center of curvature. Center of curvature obviously will be double of this center of curvature here. If we send a ray through the center of curvature, along this direction, it will retrace its path, isn't it? These two will meet at a point. My ray diagram is a bit problematic here, just let me correct it. Wait a minute. We have to maintain the law of reflection always. See the mistake I did here, you learn it from my mistake. This is normal, no? We have to take the reflected ray accordingly. The reflected ray will go this manner, clear? And these two will meet at a point, so image will be formed here. This is AB This is A dash B dash. Okay? Image is larger than that of object. Size of image is greater than the size of object. We'll define magnification is equal to h2 by h1. h2 stands for what? Height of image. Say h2 is the height of image. h1 is the height of object. Clear? Magnification is defined as h2 by h1. Here it is magnified really, and by using the similar triangle we can show that. Another thing, see, magnification, the symbol I have taken, it is not correct. This one lies above principal axis, this is below principal axis. We should take a minus sign before. Never do this mistake. Magnification will be minus h2 by h1 according to sign convention. But in these two similar triangles, you see two similar triangles are there. Which two? This one and this one. This one and this one, they are similar triangles. Or you do one thing to get a similar, like here, see, here, which one is similar triangle? A dash, CB, ABC, they are similar. 90, 90 opposite. Similar means angles are equal. You should keep in your mind. So what I want to say that by using similarity, I can easily prove that magnification AM equal to this from the triangle h2 by h1. h2 by h1 equal to this distance V by this distance U. These two similar, it can be proved easily. Clear? So AM equal to V by U and both are negative. So this is V by U. But magnification we got here earlier. Therefore minus h2 by h1 V by U. So h2 by h1 is minus V by U. Clear? This is called magnification. This h2 by h1 equal to minus V by U. This is called magnification. Okay? This is called magnification, produced by the spherical mirror. So this is another task for you. You will prove how these two are similar. Actually, similarity you don't have to think. You draw a perpendicular here, then you prove these two similar. From there you can get easily. These two triangles are similar. If you draw a perpendicular, this point of incidence be L. I am showing you triangle A dash B similar to triangle ALM. From there also you try to prove how this h2 by h1 is coming to be V by U. So understood? For spherical mirror this concept is required before you start practicing sums.